Alright guys, this is the bonus trig review. I wanted to explain some of the things you'd be writing down, so hopefully it makes a little bit more sense. So hopefully you've already written this stuff down, or you're going to be writing as I'm talking. That way you can pause the video and catch up with what I'm saying. So anyway, let's talk through this thing. So we're going to need trigonometry, which are sines, cosines, tangents, for lots of the stuff that we do, not only in this unit, but moving forward with a bunch of other units. So we'll start by looking at this triangle right here. And we're going to look at the acute angle down here in the corner. Of course, you've got your right angle and this other angle up here. So we'll look at this first one and we'll label it theta 1. So in this particular case, that means this is the opposite leg of that triangle. And this is the adjacent leg right here. Now the hypotenuse is always the longest side, as you can see that I wrote right here. And that never changes. The idea with this first part is that if you change the angle, that changes what's opposite and what's adjacent, because you're always referring to this angle. So in this case, this is opposite of this angle. So anyway, the quantity sine theta is a definition. It doesn't mean anything more than what is the ratio of the leg opposite the angle, so that's our O1 right here, divided by the hypotenuse. So sine is just a ratio. Cosine of that angle, theta 1, is just, again, a ratio, which is the adjacent over the hypotenuse. So these are just definitions of what sine and cosine means. So we labeled this theta 1. Now we look at the same triangle, and so you can see it's the same. I've just gone up here now to this top corner, and I've got theta 2. So as you can see, the opposite leg for triangle 2, or the second angle, angle 2, is right here. On the previous look at it, that was the adjacent leg because we had a different angle. So on angle 2, we've got opposite here, adjacent here. Notice that has sort of switched from the one above. And then you can see that the hypotenuse has stayed the same. So if we look at this one, sine theta 2 is the opposite leg number 2 over the hypotenuse, which stayed the same. And the adjacent over hypotenuse would be the cosine on the same triangle. Okay. Now, tangent, you may not have ever seen where it came from, but it's very simple. It just turns out very occasionally that it's helpful to divide sine by cosine. And so what you get is you take sine, which is opposite over hypotenuse, you take cosine, which is adjacent over hypotenuse, the hypotenuses cancel, and you get tangent theta, which is defined as opposite over adjacent. So a lot of people think they need to know all three, but really sine and cosine are the fundamental ones, and then tangent comes from dividing them. Hence, you may have heard this in your math class, you get SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and TOA for tangent is opposite over adjacent. Okay, so it turns out using these simple identities, we can actually work out some of the most important angles or most common angles that we're going to see, and we do that all using the Pythagorean theorem. So the first type of triangle, which I'm sure you've seen in your math class, is a triangle that looks like this. So you can already see what the ratio is going to be. You've seen this before, but let me show you why it ends up being a 1, 1, root 2 triangle. I'm not sure what you would have called it in your math class. Anyway, what we do is we take a square that would be normally side length of 1, cut it in half so you have a nice right triangle. That means each of the legs of my triangle, A and B, are equal to 1. The question is, what's the hypotenuse? All you have to do is use the Pythagorean theorem. 1 squared, which is A squared, plus B squared, which is also 1, equals C squared. So 1 squared plus 2, or 1 squared plus 1 squared is 2, equals C squared, and then you solve for C, you get root 2. So that means the hypotenuse of this triangle is root 2, which makes sense because that's longer than 1 or 1. Okay, let's move on to another very common triangle. You've got a 45, 45, 90 triangle. That tells you that A and B are going to be the same. Again, this would be like a square, where the diagonal would be a 1, which a lot of times you'll see this called a unit triangle, where the hypotenuse is 1s. It's kind of a funny way to say that. In most countries that speak English besides America, when you say unit in mathematics, you mean 1. So this is a unit triangle. That means it has a hypotenuse of 1. Anyway, to do this one, to find out what A and B are, since they're the same, we can use the Pythagorean theorem. So we have A squared, whatever that is, plus B squared, whatever that is, equals 1. So when we work through this, we end up realizing that A and B are the same number. So A squared plus B squared equals 1. We have 2A squared equals 1. Solve this for A. That tells us A is square root of a half. And your math teachers get angry when you have a square root on the bottom. I don't really care. But anyway, if you rationalize that, you get square root 2 over 2, which ends up being the leg length for A and B. Now, if you look at this carefully, this gives us a clue about what sine of 45 and what cosine of 45 is. So sine, remember, is opposite over hypotenuse. Opposite being A, hypotenuse being 1. So here we take A over the hypotenuse, which is root 2 over 2, divide by 1, and we get just root 2 over 2. Same with cosine. We take B over 1 because that's the adjacent leg to this 45-degree angle. Divide by the hypotenuse, which is 1. We get root 2 over 2 all over 1. That would be B over hypotenuse. And again, you get root 2 over 2. So interestingly, sine 45 and cos 45 are the same, and they're about 0.707, about 70% of 1. All right, so you may have seen a 45, 45, 90 triangle before, and you may have seen that relationship. The last one I'd like to take a quick look at is a 30, 60, 90 triangle. You may have seen this. Now, this one's a little bit goofy to derive. You start with an equilateral triangle, each with side length 2, and you cut that in half with this dashed line here. Now, we know that each of these angles is 60 because a triangle needs to add up to 180. Makes sense. If we cut that in half with this line, that means this leg, half of 2 is just 1, okay? So we can isolate this triangle here that has a hypotenuse of 2, this short leg of 1, and then some unknown length here. So you can see I've redrawn that here. Here's my hypotenuse. Here was half of the original length of my equilateral triangle, and then this is the unknown leg. So just like the other examples, we can do the Pythagorean theorem. 1 squared, which is the short leg, plus that unknown leg, x squared equals 2 squared. So x squared equals 4 minus 1. X is root 3. So you may have seen this ratio pop up before, and this is why that works. Now, if we scale that down, if we divide all these values by a factor of 2, your hypotenuse, 2 divided by 2 is 1, 1 divided by 2 is a half, and this root 3, which was our x right here, becomes root 3 over 2. So if we look at the same thing we just looked at above, sine is opposite, which is a half in this case, over 1. And so that ends up being a half. So sine of 30 degrees is a half. You're going to see that pop up a lot. You take cosine of 30, that would be the adjacent leg, this one here, divide by 1. So you end up with root 3 over 2 all over 1 equals root 3 over 2, which is about 86.6 or 0.866 or 86.6%. Sine 60, interestingly, if we switch to the other angle, so this is our 60-degree angle right here, everything just switches. So now this is the opposite leg, root 3 over 2, divide by 1, which is the hypotenuse. That's sine. You get root 3 over 2. Cosine ends up being a half in this case by the same logic, and you can check that one yourself. Now, you can also do this with your calculator. You want to make sure that your calculator is in degrees mode, and the way to do that is to hit mode and make sure it's in degrees. Some of you guys who are in pre-cal or calculus may be using radians, and you'll have to make sure that you're in the correct mode. Anyway, I just want you to try a couple of these. If you actually pause the video and punch these all into your calculator, you'll get sine 30 equals 0.5, which is what we got, and you'll get all these. Now, interestingly, you'll see that sine 30 is 0.5. Cos 30 is 0.866, and then if we switch to the other angle, sine of 60 ends up being what cos of 30 was, which is kind of interesting. Same with cos 60, it's a half, just like sine 30 was. I gave you some other slightly more exotic ones where you definitely can't use these triangle tricks from above. You'll have to use your calculator. You'll see sine 76 and sine 14 are these two values, and then cos 76 is the same as sine 14, and cos 14 is the same as sine 76. Now, what we call that is complementary angles, and my little bar here is covering that up, but you can see, that's why I want to go away. You can see here, angles that add up to 90 degrees are called complementary. So you'll always get the same sine and cosine values. They'll just switch when you go from one angle to the next in a right triangle. So anyway, that was your bonus trig review. Hopefully that helped you after you had filled it out. I know it's a little bit messy, but hopefully this video helped you understand what was going on. Thanks for watching.